let's get started. So today, I'm just going to be giving a little bit of an introduction to this category theory formulation of QFT. So these generalized symmetries um, are going to be using some concepts from category theory at some point. Um, so I thought it'd be nice to start off with just introducing some of these ideas so that when we encounter them later, they're maybe not so foreign. Okay. Um, so we won't talk so much about any generalized symmetries or anything today. What I'm going to do is give a brief introduction to some ideas from category theory that we might need, and introduce particularly the idea of monoidal categories. And then I'll give some really basic stuff on how we can actually use these ideas in the field of topological quantum field theory, just as a little toy example to see why maybe some of these ideas are interesting. Okay, so we're going to be interested in generalized symmetries. And in the same way, we have ordinary symmetries. We have, when we talk about ordinary symmetries, we talk about groups and representations. When we talk about generalized symmetries, instead of talking about groups and representations, we talk about something called a fusion category. And we won't really discuss what this is today, but it's something we'll encounter later. Now, naturally, category theory has a reputation for being quite abstract. And for most people, especially in physics, a lot of the language and terminology is probably quite unfamiliar. People think it's quite esoteric and maybe needlessly technical. Um, but maybe as a historical analogy, um, it's interesting to think about group theory. So obviously, in the modern day, if we think about group theory, it basically underpins everything we do, right? We look at symmetries, we look at groups. It'd be difficult to think of how we would formulate physics without group theory. But back in the 1920s, um, Wigner and Weil introduced groups into physics. And this was actually met with a lot of resistance from other physicists at the time. Particularly, Schrodinger really hated this idea, and he talked about this plague of group theory, um, which they call the Gruppenpest in German. So they really thought this idea of groups and representations was way too abstract and way too formal to be of any use. And obviously today, that basically underpins everything we do. So maybe we shouldn't be off-put by the abstractness of categories, because as we'll look at, they already have some utility. So my goal for today is to start with some basic ideas in category theory. And then we're going to look at some simple applications. And we won't go super into depth. We'll just skim through some really basic ideas, and hopefully just as a bit of a motivation of why we might want to use this stuff going forward. So I'll also tell you some nice resources that might be useful if you want to learn more about this stuff. So um, there is a book. Oops. There's a book called Topological Quantum, which gives a nice a nice look at these topological aspects of physics, but it doesn't it avoids talking about things in terms of categories, but it basically uses the same constructions. So if you're scared of like the technical stuff, this book sort of avoids the technical stuff to give you a real feel for it. If you want to go a bit deeper into topological quantum field theory, there's a nice set of notes by Carcaville and Runkle. But these are a bit more technical. If you're interested in some of these axioms and how these axioms arise to describe topological quantum field theory, there's a nice old book by Tia called Geometry and Physics of Knots. And a really nice introductory book for category theories is Category Theory. Oh, sorry, no. Categories for the Working Mathematician. Um, by McLean. And this is a very standard introductory text to category theories uh, if you want to learn more.
Just quickly, we
Um,
can. You mind if we interrupt you during the
oh, yeah,
presentation?
of course. Yeah, feel free to
Can
interrupt
you
the.
also remind us which lecture notes we're following as
Ah,
well?
yes, yes.
Cool.
Um, so the reading group, we're going to be following um, Simon's lectures on on categorical symmetries, um, which is 24110908 on archive. So yeah, I'll also post the reading group notes. Sorry, the readings that we're actually following to the page. I forgot to do that. But this is the set of notes we're loosely following. Okay. So maybe let's get stuck into things. Yeah. Okay. So the idea behind categories is we really want to try and generalize the idea of mathematical structures. So usually if we think about different fields of mathematics, we study different sorts of structures. So for example, if we have set theory, of course, we study the structures of sets and functions. If we have graph theory, we of course study graphs and graph homomorphisms. And then if we had group theory, we study groups and of course group homomorphisms. If we wanted to do differential geometry, we study manifolds and smooth maps. And of course, we can keep writing down all these different fields of math. Um, but the idea is behind with category theory is that we want to look for maybe some common notions that all of these structures have in common and see if we can maybe make a general statement um, that we can apply to maybe multiple fields of math. So, for example, maybe if you study group theory and if you study algebra, there's different various isomorphism theorems. Maybe we can prove some sort of isomorphism theorem in a general framework that can apply to multiple different areas of math. Um, so I guess the important thing is, though, when I talked about these examples here, I didn't just talk about the objects, sets, graphs, groups. I also talked about the functions or the maps, which give relationships between these different structures. So, if you want to study sets, there's basically nothing interesting you can say about sets if you don't have an ability to compare sets. There's no point studying graphs if you can't compare graphs. What's the point of studying sets if you don't have functions, you don't have subsets, you don't have orderings? Why would you want to study groups if you don't talk about images, kernels, subgroups? It doesn't really make sense. So the key thing is that the relationships between these objects are actually more important than the objects themselves. So in fact, you can actually treat objects as a black box and get all the information you need about them up to isomorphism just by studying their relationships with other objects. So a really basic example is sets. So if I have, let's say, a few sets, and I won't tell you what's inside them. Let's say this set is A, this is B, and this is C. Now, because they're sets, they also have functions between them. So let's say that maybe there's a few functions from A to B. There's a function from B to A, and I'll call this one G. There's maybe a function from C to A, which I'll call H. And maybe we also have some functions from A to C. Okay, so we actually don't know anything about these sets. These are just black boxes. All we have is these functions. And if I tell you that these are all the functions between these sets, what can we say? Well, let's look at this map G, for example. So G here, maybe I'll write it over here. G is a map from B to A. And I said that this is all the possible functions we can have. So this means that there's only one function that maps elements from B to A. And we know just from basic combinatorics that if A has n elements and if B has m elements, then there are n to the m possible functions. So, and these are all the ways of sending elements of B to A. So what does this tell us? This tells us that A only has one object. It's a singleton set. So, and then because there's only one object in A, so there's only one object in A, and we have four possible maps. These are like four possible embeddings of this element in A into B. Well, then we know that B must have four elements. And likewise, you can tell that there are only two elements in C. The only thing to note, though, is that we can't tell what singleton set A is. We don't know what element this is inside A. But that doesn't actually matter because in set theory with no other structure, all sets with the same cardinality are isomorphic. So just by looking at the relationships between these sets, we have all the information we need to determine the internal structure of the sets up to isomorphism. And for sets, that's just the cardinality. So the idea is we want to generalize this, and it will actually be quite powerful because we can probe the internal structure of more complicated objects indirectly just by seeing how the objects relate to other objects.
Just quickly, with this example here,
Yeah,
are you saying that these are all the possible functions on this
yeah,
black box set? Like you're
yeah.
listing all the functions.
Yes, I'll list out all the
These are,
possible functions. Yeah,
these are all the possible functions.
yeah,
Okay.
yeah.
Yeah, that makes sense. Thank you.
Okay. So let's then talk about categories. So we have this motivating example. So let's actually formally define a category. Um, so, oops. So a category, and I'll denote it with math C, consists of two parts. There is a collection of objects, and I say collection to avoid any problems of having sets of sets and stuff like that. Um, and we call this ob C. And we have a collection of what we call morphisms, or sometimes they're just called arrows between objects, and we call this more C, the morphisms of C. Um, we also have operations called domain and codomain, and basically for every uh, morphism, it just assigns yeah, the domain and the codomain in the exact way you would expect. And often we just denote this as the standard notation. And these things have to satisfy a few axioms. So for all objects A, we have an identity morphism, which is just a map from the object to itself. Um, we have a composition operation, which we would call like circ, like the normal sort of composition. And this is just a map that sends morphisms to, you know, f of g or f after g. And this is defined if and only if we have a good match between the domains and the codomains of these objects. We also have some conditions on the identity and these functions. Just the usual thing that you would sort of expect an identity to define. And we also demand that we have associativity of composition when these individual compositions are well defined. Okay. Um, so this might seem a bit of a lengthy sort of definition, but really this is sort of the minimal structure that we need to be able to start saying anything interesting. We have a collection of objects, a collection of morphisms, and we have a well-defined notion of composition of functions or morphisms. So you can try and compare these ideas to what you would have in set theory. It's a nice analogy to always fall back onto.
Could you
So
repeat again for number three? So there
yeah,
was dom meaning like domain, and then is that co? What's
codomain,
what's
yeah.
that? Um,
Um,
did
so
you write COD? They're called COD.
yeah, COD. So
Okay,
if I
it's just a
have
bit
like
hard to read. That's all.
DOM of F would just be A, and the
Yeah.
codomain of F would be B.
Oh, so these are operations that act in each of the morphisms.
Yeah, yeah. It's not so important. This is just like technical language, right?
Sure.
It's just
Um,
yeah.
but just I want to be clear in terms of notation. Is it COD?
Yeah, COD,
Okay,
short
that's all
for
good. Thank you.
codomain.
Yeah, that's fine. I thought it was just a fancy symbol you might have written or
No,
something.
sorry. Yeah, if anything's unclear with my atrocious writing, just let me know. Okay. So one thing that we have that's interesting is this existence of the identity morphism. Um, and because we have these identity morphisms, turns out we can actually get rid of the objects themselves if we really wanted to. We don't actually need to talk about objects at all. Because if we think about our example from above, where we had these sets, right? And I didn't draw the identity maps before, but I could this time. Uh, I'll just do this. So there's actually secretly also these maps, right? That just map the set back onto itself. And because we have these things, what we could actually do is just get rid of these objects themselves and just think of everything in terms of composition of maps. So, so this would be the identity on B. I think if I remember which way I labeled them, yeah, A, and the identity on C. So, um, yeah, because we have an identity morphism, we can just describe everything in terms of compositions of morphisms and identity morphisms. Okay, so let's think about a few examples. Um, so we have the category of all sets and functions between them, and we call this set. Um, Usually people use bold text or an underline to talk about a category. Um, we could have algebraic structures, where instead of functions, we're going to have some sort of homomorphism. So we could have for groups, we have the category group, which we just write GP, which has groups and group homomorphisms. We have for rings, we'd have the category of rings with rings and ring homomorphisms. Um, if we have vector spaces and linear maps, and I'll say over K, over a field K. So this could be like R or C or something. We denote this as vector spaces over K. Um, if we want to talk about analytic structures, we have topological spaces and continuous maps, and this gives us the category top. If we had metric spaces, and we could have non-expansive maps, so things that are either well, they're either contractions or not expanding or not contracting, but non-expanding. And this would give us met. Um, to be specific, if people are interested, um,
Sorry, by non-expansive, do you just mean something which is not like a scale transformation?
yeah, I just mean this condition. So if I
Okay.
perform a map, the distance between points strictly, not strictly, well, strictly don't get further apart. They either stay the same distance or get closer together. And this turns out to be the appropriate sort of maps to talk about on metric spaces. And of course, you have, you know, manifolds and C infinity maps, and this gives the category of manifolds. Okay. Um, So for all of these examples, all of these are functions, right? These morphisms are all functions. But this doesn't have to be the case in general. We can have any sort of relationship that satisfies the axioms, and this counts as a morphism. So, for example, we could also have things like relations and orderings, and these would also be able to give you a category. And this is actually more general. So, if you go back and think about set theory, um, functions in set theory are actually just relations. You know, they're just relations where for each A and A, it relates to exactly like one B in the codomain. So they're sort of like one-to-one maps. If you think about relations, it's like subsets and stuff like that. That's just a technical aside, but you can do more general things than just functions. Okay, let's try and maybe pick up the pace a bit. So let's talk about functors. So as we've just seen, we've been able to boil down some common ideas underpinning these mathematical structures to just the idea of relationships between objects. So this will be quite powerful, but let's see how far we can sort of take this idea of abstraction. So one could maybe imagine that categories themselves are also some kind of mathematical structure, right? So could we have a category where the objects are also categories? And if we wanted to have a category, we'd also need an idea of a morphism between categories. And the appropriate idea of a morphism between categories is something called a functor. So let's introduce this. So if I have two categories, then a functor is a map. Well, it's a pair of maps, which we call F for both. And this is technically a map from the objects and a map on the morphisms. But we just usually just use this notation because it's clear what we're talking about. Sorry. Okay. And these have to obey a few properties. They have to preserve domains. So the domain they've got to preserve codomains. And they've got to preserve identities. And finally, they have to preserve composition. And sometimes I'll just not put like the circle between composition. I'll just use juxtaposition, and hopefully that's clear that this is composition. So really, these sort of arise quite naturally. These are like the basic, minimal, sensible conditions that we need to have any sort of structure, right? Um, you know, if we have some sets, we have some maps, you know, um, if I want to map this over to, some different category, you better hope that the domains before and after agree. You better hope that the codomains before and after agree. You got to hope that the identities agree because we said that we can replace all the objects with identities. It's sort of like this minimal ability to preserve the structure of the category. Um, hopefully, you'll believe me when I say that. Okay. Um, so as we said, if we want to talk about a category of categories in some sense, um, you should be able to see that we can have a notion of composition of functors um, just following from these definitions. Again, you just got to have agreement of the domains and codomains and stuff like that, and you can define the usual notion of composition. Um, so let's think about maybe a few examples. The really basic example is called the forgetful functor, and we often call it U, and it's usually a map from some category back to set, which forgets the structure of the original category. So, for example, we could have a forgetful functor mapping from group to set. So it sends a group back to its underlying set, and the group homomorphisms just become ordinary functions. We sort of forget about the group structure. We could also have one from metric space to, for example, topological spaces, and you forget what the metric structure is. So as you remember, when you have a topological space, that's like your basic level of structure. You can impose a metric structure on top of that. So you can sort of just go back to a basic structure. Um, there's nothing too crazy there. Um, maybe a more interesting example is the power set functor. And this is a functor from set to set. And of course, as you know, power set, it will map a set to the set of all subsets of that set, which is a lot of times of saying set. So I assume everyone remembers what the power set is. And then hopefully you can agree that this is a map that sends any set to another set. And of course, you can check that it obeys all the appropriate notions of composition and stuff like that, and actually does give you a functor according to these axioms. But I think I will not go through fleshing that out um, just because of the time. But I also have some notes that I've typed up about this stuff, which I'll also upload later if people are more interested.
I just
Okay,
one thing with the power set, like
yeah.
it doesn't need to be a functor, right? Like it can be a functor. Whereas say like the forgetful functor needs to be a functor because you're going from the
Well,
different categories.
I mean, this is what we call the power set functor. Because remember, it's not just a map on the subsets, from the sets to the subsets, it's also a map on the functions. So there's a specific action this has that makes sure that you get functions on the subsets in after this mapping. So it's okay that it's a functor from a set to itself, from a category to itself, right? It
Oh,
doesn't
I
have to
see.
be
So
to a
like
different category.
okay. But I see like there's functions implicitly like
Yes. So
here as well.
anytime you have a functor, it's not only an operation on objects, it's also an operation on morphisms. Um, so there's also, this maps sets to sets of subsets. It also has a particular action on the functions. I have a nice diagram I've drawn in my notes that you can look at if yeah, because it's a bit confusing. But yeah, I don't know if I have time to go through if we want to get to the juicy stuff.
Okay. No, thank you.
Okay. Um, yeah, so let's jump to the sort of categories that we'll be interested in. So let's look at monoidal categories. Okay, so things like set, that's a pretty basic sort of mathematical structure. We're going to be interested in categories that have additional structure. So particularly what we want is some idea of a notion of a product between objects. And because we have a product, there has to be some identity, a notion of an identity, the identity of multiplication in this product. And when we have these things, we call these categories monoidal categories. So maybe a few motivating examples. Um, if we have just some category C that has like an underlying set structure, then you can use the usual Cartesian product and some singleton set, and this gives you something called a Cartesian monoidal structure. So hopefully you can convince yourself if you have a set and you multiply it by a set of one object, you sort of get the same, an isomorphic structure back, right? Um, in metric spaces, for example, if you have two metrics on different metric spaces, you can take this sort of Cartesian product of metric spaces and you can define a new metric on this space from these original metrics. Particularly interesting to us is Hilbert spaces. And these have a monoidal structure given by the tensor product. So if we have A tensored with B, we also have the unit of multiplication is, if we're working over C, is C, the complex numbers. Of course, if you remember, this is like C is a one-dimensional vector space, right? One-dimensional complex vector space. So if you have, C tensored with something, it's going to be isomorphic to itself, right? If you think about, the usual sort of tensor product of matrices, if you tensor this with something one-dimensional, you're going to get something with the same dimensions back. Yeah, this might be a bit weird if you're seeing it for the first time, thinking about a multiplication between Hilbert spaces, but hopefully, you've seen this tensor product of matrices before, and it should sort of make sense. So yeah, these few examples all obviously have this common sort of structure, and this allows us to define something called a monoidal category. So a monoidal category is a triple. So we have our category, we have our multiplication operation or our tensor product, and we have some sort of identity or unit element. And there's also three isomorphisms. Well, I'll also say that this is a map like this. And we also have some isomorphisms alpha, which encodes associativity. We have this lambda, which we call left, and we have rho, which we call right. Where alpha is a map from A times B times C. I think it should be tensor, sorry, which just shifts the brackets, right, of associativity. lambda is something that sort of encodes this multiplication from the left with the identity, and rho is this right multiplication with the identity. And this is sort of a technical thing. And basically, the idea is we need these things to ensure um, that we have the right notion of associativity. So we have that alpha satisfies something called the pentagon diagram, which I'm not going to draw in full detail, but the idea is that it's all the possible ways um, of performing like associativity between a few objects. So if we start with this object, we can act with this alpha on various triples of these, and this pentagon diagram just shows that no matter how you do your associativity, everything agrees. So this is for consistency of associativity. I won't draw the full diagram to save a little bit of time. And we also have a triangle diagram that says that these left and right multiplications agree with associativity. This is a
Could you just
technical,
say, sorry, could you just say quickly what you mean by isomorphism in this context? Because there's not necessarily a group structure, is there?
Uh, you mean in terms of like alpha? Like,
Yeah. Are we just calling that isomorphism? Because I
yeah,
was
yeah,
like,
yeah,
so we're calling alpha, lambda, and rho isomorphisms.
yeah, yeah.
But okay, but they're nothing more than just the morphism. They're just a morphism, right?
Uh, yes, yes. They're morphisms on these objects. Yes.
And are you
Um,
using the word isomorphism because they're meant to be some sort of invertible condition
uh,
or something like that?
yeah, yeah. Because I guess, if you look at this alpha, right,
Hmm.
there should be an inverse, right? There's some sort of structure preserving map. Um, so yes, it should be invertible as well.
Are lambdas invertible? Oh yeah, they should
Uh,
be because it goes on to the left. I see. They
yeah,
should append like an identity. That
yeah,
makes
yeah,
sense.
yeah, yeah,
Also, when you were saying like in the thing above with the example with the Hilbert space,
yeah.
are you saying that C should have cardinality of one? What do you mean
As a
by
vector
that?
space,
Oh, you mean like dimension? Yeah,
yeah,
okay.
yeah,
Oh, that's all
yeah,
good. Thank you.
yeah. Okay. Um, so yeah, again, this is a technical definition, and maybe it'll be a bit nicer when we actually look at some real examples, which hopefully we will have enough time to do. One important thing to note is that sometimes we have a relationship like this, where we can just swap out objects in the tensor product, and these things are isomorphisms. But this isn't actually always the case. So the idea is we want to be a bit more general than this in some cases. So because you can also, this is like a multiplication, right? You can also think of a really basic example where this is not true. And if we thought of like function composition as a multiplication in some abstract sense, obviously um, G composed with F is not the same as F composed with G. It just doesn't match up in general. But more interesting for physics is with this stuff, you can have ideas of like braiding or stuff with fermions, where if you swap things around, you don't necessarily get the same object back. Um, so if we okay, I'm going to skip over this. Yeah. So let's yeah, let's go next to topological quantum field theory. because I think this is where some of the interesting stuff is, and that I'm a bit concerned about time. So, okay, so let's
Do you have an
try
idea of
and
the timing, just quickly?
well,
Are we going to go to half past?
uh, I was hoping to finish at 10, honestly, but I mean, I have a little bit to get through, but I can skip over some bits. So maybe
Okay.
we'll try and aim for 10 past or quarter past
Hmm.
if people are interested. Okay, so let's see how we can sort of apply some of these ideas in practice to some physics. So recall that we can describe a physical theory in terms of the path integral, right? Um, where here we have phi being some map from some manifold to some other manifold X. Um, for example, we could have a map on R4 to the real numbers, and this would be a scalar field. And we use this path integral to formulate correlation functions. We can also have observables, and these are functions from the set of field configurations to the complex numbers in general. So you could have various different observables. For example, you could have something like just phi. You could have the derivative of phi. You could have something like phi squared, blah, blah, blah. Um, and that obviously this is for a scalar field. You know, if you had gauge theory, you could also have things like Wilson loops as different observables. And then recall that we can have correlation functions, which we define like this. So sort of the expectation value of these operators. So these could be your normal sort of correlators, your two-point functions, and stuff like that, depending on the field content of your theory. So if this is, I've put G here, and this is like our metric. So if we're independent of our metric G for these correlation functions, um, then this means we're looking at a topological quantum field theory. So stuff doesn't depend on the metric, it doesn't depend on distances, it just depends on the topological information associated with the manifolds. So, for example, we have Chern-Simons theory, which people have probably heard of before, where we have some action that looks like this. And this is independent of the metric. So this is a purely topological theory. So one could think about maybe what sort of structure we would want to look like, what we want to look for if we wanted to describe a topological field theory. So what are some basic ingredients we might need to be able to describe a theory? So there are a few ingredients we might want. So if we have, for example, a space-time slice, right? And we call this E. And I'll say this is an n-1 dimensional manifold. We would like maybe a Hilbert space of states on E, right? So, and we'll call this Z of E, some Hilbert space of states on E. And these will act as functionals on the fields, and I'll mention what I specifically mean by that soon. We would expect, hopefully, if we had some space-time slice on a manifold like this. So if E is some disjoint union of E1 and E2, then maybe we'd hope that the total Hilbert space of E is the tensor product of the Hilbert spaces of E1 and E2. And we can actually see that if we have something like this, then we know that we can do a disjoint union with an empty manifold, the empty manifold, right? And this is just equal to the original manifold. And this directly implies that we should assign to the empty manifold just C. And hopefully you can see that from this sort of assignment. Okay. So if we had a manifold with some boundary E, then so I have some manifold, maybe it's got a hole of some description in it. And this is M, and this is E. Then we would like this manifold to assign a particular vector in E. So what does this mean? We can think of this as M encoding the evolution of state via the path integral. So you can really think of M as like a history of the system. So when we have M, we're specifying a history, and this should pick out a particular state in the Hilbert space on E. So if we know the history, we should be able to specify a particular state. What this means from the path integral point of view is that Z of M acts on our fields in a particular way. Um, so we can integrate over configurations such that the field on this boundary is a particular field configuration. So again, we can sort of use this fact to show that if we have an empty boundary, so some maybe closed manifold M, then we assign to it just a complex number. So when we have a closed manifold, maybe this acts as something like an inner product, which we'll talk about in a second. Okay, so if we have maybe some E, and let's say we sort of extrude this and extend it over time from maybe some initial E to some final E. So if we say M equals E times an interval, what we will do is we'll assign orientation to these boundaries so that our orientation always points outward. And then you can think of the boundary of the manifold as being E with E bar, where E bar denotes the opposite orientation. Okay, so then this would mean from our factorization property that we expected above, then we would get that Z of M is some element in E tensor, sorry, H of E with H of E bar. So in other words, the interval joining these two cobordant boundaries can be thought of as an evolution of these slices. So it's a map between some initial vector space and some final vector space. So this means we sort of expect some identification uh, with E, um, with the Hilbert space on E bar, with sort of this dual space. So we're sort of, this orientation reversal sort of turns bras into kets. And this M will be called a cobordism. So then if we had maybe a manifold, um, let's say M prime, and we have another manifold M where they have the same boundary. M prime, M prime bar, because they've got opposite orientations. So if they have the same boundary with orientation reversed, then we can sort of think of this as an inner product, so that Z of M disjoint union with M prime is sort of some notion of an inner product. Um, okay, we also have like a cutting property that we'd like. So I'll just draw the picture maybe. Um, is that we would like, if we have some surface like this, and we have another surface that we embed into here, we should be able to get um, some sort of splitting of our surfaces. And you can think of this as like a sum over intermediate states in the path integral. So you can sort of split up your evolution. But because of time, I won't write out the full details there.
Wait, just
So
quickly,
yeah,
which of these ones are wish lists? So you're saying, like you said, for
well,
example,
yeah,
the inner product stuff you said was like, this is something we desire. Are all of these properties we desire for the
these are sort of properties we'd
partition function?
sort of expect from a theory. Um, you know, well, if we have a space-time slice, well, if we want to do any sort of physics, we want to assign a Hilbert space to the space-time slice. If we have two, you know, disconnected, you know, from the point of view of the space-time slice, if they're disconnected manifolds, then we'd kind of hope that the Hilbert space is factorized.
Do we
Um,
expect this for quantum field theories or is this TQFTs?
um, some of these for quantum field theories and some for TQFTs specifically.
But they should all. Oh, okay, okay.
Yeah,
Um,
yeah.
do you know which
I
ones are
mean,
which?
like these, for example, I guess you would hope would happen in a general quantum field theory. But some of these um, get a bit more complicated because, like, for example, there's additional structure when we have a cobordism, right? Um,
Hmm.
at the moment, we have no additional structure. Like the cobordism, the topological structure of this M is all that matters. So you could, and I think in the notes they actually look at more complicated structures with like a metric and stuff like that. So then if you had things like that, there'd be more assumptions you need. But this is at the
I
moment, this
see.
is just like the sort of basic things you would expect if you wanted to have a topological theory, right? You would need an assignment of states, maybe a nice factorization property. Topologically, you would want, if we know the history of our system, which in this case, the only stuff we need to know is the topology. We'd hope that this specifies us a vector if we know the history of our system. Um, so these are sort of the basic things we'd expect. But the
Okay,
idea
thank you.
is that if we use categories, this stuff actually just emerges naturally, um, almost by definition. So you can formalize this, and this gives you a tiers. axioms for TQFT. And turns out, yeah, this can be described categorically. So we define an n-dimensional closed oriented TQFT is a symmetric monoidal functor Z mapping from the category of Bordisms to the category of vector spaces, complex vector spaces. So that's why I suggestively wrote Z up here. You can see it's a map from manifolds to vector spaces. And because these vector spaces, Hilbert spaces, have a natural tensor product structure, these Bordisms have a natural tensor product structure given by this disjoint union. This functor preserves these things, and a lot of these properties we expect just fall out naturally. So I'll skip some of the technical stuff here, maybe, so we can get to some examples. Well, maybe let's do one simple result. So my claim is that most of the desired properties above follow immediately from this definition. So of course, like the things like the factorization and stuff like that, that happens naturally because there's a monoidal structure on both of these categories. So
So could you also say what do you mean by symmetric? Like, what does it mean to this
yes,
is
I
symmetric?
sort of skipped that before. The symmetric part means that there is um, some other map um, that obeys some compatibility conditions with these alpha, lambda, and rho, which I skipped over because just for time, but I have it nicely written out in the notes, which you can look at after if you want.
And then is Bordism manifolds with boundaries, or what is
So
Bordism?
so the manifold the Bordism is these M's, these evolutions. Um, so yeah, you can see that these we say that this E and this E bar are cobordants, I guess, because they yeah they are the boundary of some manifold M. So the idea is we're mapping between literally these manifolds to, vector spaces or Hilbert spaces. Um, because I'm conscious of the time, I'm just going to do one very. I had an interesting calculation that I wanted to do, but I don't think I'm going to have time. But maybe I will. Uh, well, I'm gonna. Okay. So let's state a few results, maybe without proof, just for time, unless people really want me to go through. Um, when we have this functor or this TQFT, then we actually have that Z of E is finite dimensional for all E in the Bordisms. And we also have that Z of E is isomorphic to this dual space. So this is quite nice. So this means that the Hilbert space on this space-time slice is finite dimensional. And this is what makes TQFT actually like somewhat tractable in some cases, because you have a finite dimensional Hilbert space. There's a nice proof of this, but I don't think we're going to have time to go through it, but I have it nicely written out in the notes if you're interested. But this also has another corollary. If we have E abordism, then Z of E cross S1 gives you the dimension of Z of E. I have the proof, but pictorially, you can sort of think of, let's say, a slice E. You can sort of think of maybe extruding E, and because we have these orientations, you can sort of think of maybe stretching this out to look something like E times S1. And because these have opposite orientations, you can sort of take an inner product and stitch these together. And this gives you some sort of idea or some notion of a trace, and it gives you the dimension of your original space. I have a nice proof written up, but I think I want to almost wrap up and just say maybe a few comments. I really wanted to cover an example that they actually lead off with in the notes that we want to cover, um, talking about homology and stuff like that, and how to actually describe these vector spaces for an example of a gauge field. But I think maybe I will just give a bit more of a practical, simple example. Let's consider a gauge theory where we have a discrete gauge group Zn, and let's suppose we have a spatial slice that's a torus. Then what we can do is actually compute the partition function on this torus. We can use our factorization of Hilbert space properties, because we know that torus is S1 times S1. And I have maybe some working in the notes, but you can show that Z of S1 actually gives you, it's classified by the first homology groups of S1, which I will just state because I don't have time to really go through the technical details. So you can show that this is a vector space generated by this twice because it's S1 cross S1. And we know that this is the same as the vector space generated by Zn. So what does this mean? Because we're thinking about a torus, if we had particles, these would be like sort of punctures in the torus. This implies that the ground state degeneracy of the torus is n squared, because the dimension of this is n, and the dimension of this is n as well. And this is actually like a non-trivial fact that the vacuum or the ground state of the torus is n squared fold degenerate. But actually, if we think of everything in terms of functors and topological information like this, you can just do it quite simply. I mean, this step is maybe not so simple, but I didn't have time to really break down that, but it's in the notes. So if you're interested, I'll attach these somewhere. So this is like a non-trivial sort of fact, but it basically comes for free just from these axioms. And you can actually extend these sort of results to higher form symmetries and stuff as well. Um, and this is really nice because on the torus, I guess eventually you want to consider things like anions and fusion of different types of anions. So this categorical construction is actually quite nice, especially when you move to non-abelian stuff. But I think I should wrap up there because we're quite over time. So yeah, I might stop there, and if anyone has any lingering sort of questions, we can answer.
Oh, yeah. Thank you for that. I just want to ask something just about the last thing. What do you mean by the group generated by the homology? Why would you not? I'm just confused about what the difference is compared to just writing the homology group. Like, what
Yeah,
exactly
I'm
do you
just saying
mean?
it's a complex vector space.
Oh, it's a vector space. Oh,
Yeah,
so
yeah.
that's not
So
like
that's what
group
I'm
generator
sorry, when
notation.
I'm saying these, I mean the like the complex span.
Oh, I see. Thank you.
Yeah.
That makes more
I sort
sense.
of skipped over that a little bit because I I had a full sort of explicit construction of this and showing why this is true. Because it's actually non-trivial how these
Hmm.
homology groups arise. And they in the notes they sort of just state it, so I actually kind of really wanted to explain it a bit, but I have it typed up and I'll attach these notes to the page so people can look at like my actual notes, which are a bit nicer.
Yeah. I mean, I guess we don't have to follow in like strict order. Like we can pick up from where like the last one leaves off, like make alterations,
Well, I mean,
whatever.
the entirety of this first section of this these notes that we're following are basically this sort of computation.
I see.
Um, so yeah, uh, yeah, like I think like the last thing they say is calculate Z of S1 and the action of Z on the board is given by a pair of paths and stuff. Um,
Okay.
but yeah, I have some explicit calculation of this written out if people are interested. So this was probably a bit dense of a talk because we introduced a lot of this category stuff, but I think at least like the next few talks might be a bit more down to earth than this, I think. But yeah.